So the first type of calculation we do is to calculate Kc values. Now, you might think we've already done that, but we haven't. All we've done so far is work out Kc expressions, or like work out what the fraction looks like. What we're trying to get here is an actual number, an actual value with units that gives us an idea about our equilibrium position, whether it's a big number or a small number. So you might think, okay, that's not too hard. Surely just like get a Kc expression and plug some values in. Like that would be true. But that would be quite basic, quite easy to do. Generally, the questions you get involve doing a little bit of working out, a little bit of logical reasoning to try and work out what those equilibrium concentration values are which you need. Now, this might seem a wee bit tricky, but it's easier if you actually look at an example first. What you've got at the top of this second page, which is page 30, is a number of steps for you to work out, like a systematic method to work out Kc expressions. But we're going to just dive straight in and see it in a real example. So this is kind of what it would look like in the exam, for example. It gives you an equilibrium process or reversible reaction. So this is the Haber process again. It tells you 0.025 moles of nitrogen is mixed with 0.01 moles of hydrogen in a volume of 2 decimeters cubed at 150 degrees C. At equilibrium, the amount of ammonia formed is 0.0006 moles. Deduce the value of the equilibrium constant Kc. So clearly there's a little bit of working out going on here. They're giving us a few numbers, but maybe not every number we need. So where do we start? Something you might want to do just to kind of get it out on the page is just do the Kc value, or sorry, the Kc expression. You don't necessarily need it to the very end, but that might be a good starting point. So Kc, as we saw on the previous page, is going to be NH3 squared over N2 times by H2 cubed. So that's our expression, but what we need for that expression is concentration values. To get NH3, N2 and H2 into this fraction, we need to have what their concentration is at equilibrium in moles per decimeter cubed. Clearly, I don't have that yet. I've got a wee bit of working out to do to work out what those are, what those values are. So let's go through it step by step. Step 1 says record the initial mole values of each substance given in the equation. So basically what it means is try to transfer all those bits of information from the question into like a table. So this is the table we'll use, and probably would recommend you using it. Obviously there's a few ways of laying out your working out, but this is quite a nice systematic way of showing it. We've got our initial moles, our reacting moles, explain what that is in a second, equilibrium moles and equilibrium concentration. That's the target there, if you can remember. We're trying to find the equilibrium concentrations of our reactants products, which will allow us to calculate Kc. All I've got at the minute is a couple of initial moles and one equilibrium moles. Because if we look through the question again, at the start I've got 0.025 moles of nitrogen, so the initial moles of it is 0.025. I've got 0.01 moles of hydrogen, so its initial moles is 0.01. And because those are my reactants, I'm pretty safe to assume that I didn't have any products at the start. I mean, you can maybe get examples which are slightly trickier, where you have a mixture of reactants and products at the start, but because they haven't told me anything about ammonia at the start, I can assume there's nothing there. What they do tell me about ammonia though is at equilibrium number of moles of it. At equilibrium, once the reaction's taken place and the source stabilised, you end up with 0.0006 moles of it. So I'm putting that in the equilibrium mole section of ammonia. So again, don't worry if you don't know where you're going here, but hopefully you see all we're doing here is transferring data from the question into this table we set up. Step 2. So this is sort of the fun logical problem solving step here. What you have to do is deduce or work out the equilibrium mole values for each substance. So I'm going to talk you through how you approach that. The key bit is to look for the column where you've got an initial moles and an equilibrium moles. In this case, it's the reactants, though you might look at other cases where it's, in this case, the product, in another case, it might be the reactants. So at the start, I had no moles of ammonia, but at the equilibrium, I had 0.0006 moles of it. That's where the reacting moles rule comes in. That means that over the course of this reaction, or this equilibrium, I have gained 0.006 moles of ammonia, just increased. The knock-on effect of that is that that's caused some of the nitrogen and hydrogen to be used up. Because I can't just make ammonia out of something, it has to have come from these two things reacting together. The question now is, well, how much of these things did get used up to make that ammonia? And that's where a kind of our mole ratio comes in, a bit like when we did mole questions back in AS and GCSE. The ratio here is 1 to 3 to 2. I've made 0.006 moles of ammonia, therefore I must have used up some of these, and the ratio guides me to tell me how much of each of these I've used. For example, it's a 1 to 2 ratio from N2 to NH3. Therefore, if I've made 0.006 moles of ammonia, I must have used up half that amount, 2 to 1 ratio, for that to take place. So instead of me using up 0.006 moles of N2, I've only used up 0.003 moles of N2, 1 to 2 ratio. Similarly, it's a 3 to 2 ratio for hydrogen being used up to ammonia being produced. So maybe a wee bit more working out here. If I take that 0.0006, if I divide it by 2 times it by 3 to go from a 2 to 3 ratio, that would mean I've used up 0.0009 moles of hydrogen. So hopefully you didn't get lost there. Another way of looking at it, if we look at the numbers I've ended up with, a 1 to 3 to 2 ratio of nitrogen to hydrogen to ammonia would make sense if I reacted 0.0003 moles of nitrogen with 0.0009 moles of hydrogen, because it's a 1 to 3 ratio. And if I was trying to work out how much that would make, I'd do a 1 to 2 ratio, which would be 0.0006. So it kind of makes sense once you get the numbers down. The challenge is to try and work backwards from one of the columns to work out what the other ones are, but you're just using your mole ratio to work out what the missing values are. So if you think about the implication of that, so this column's all sorted now, because I know I made this amount and that leaves me with this amount because I started with nothing. But if you think about this is what I've used up of my nitrogen and hydrogen. That's not actually using up all of it. I've still got quite a bit of this left. How I work out what I've got at equilibrium is I'm going to subtract that reacting moles value from the initial moles value. So 0.0003 taken away from 0.025 gives me this value, and 0.0009 taken away from 0.01 gives me 0.0091. Lots of knots there. And that's pretty much most of the working out. That's the hard bit of this calculation. Doing that wee kind of deduction or by logical thinking to work out what the equilibrium moles are. Now, the temptation always here is to go straight from this, think, okay, brilliant, I've worked out my equilibrium values, I can chuck my values straight in here. But we can't, if you stop a second. This Kc expression only works for concentration. Remember, these square brackets means concentration in moles per decimeter cubed. This is just moles, so I haven't got a volume. If I look back to the question, something I maybe skipped over, this is taking place in a volume of 2 decimeters cubed. So what I have to do is work out what these mole values are as concentrations. Not too tricky to do that, that's step 3. Convert mole values into concentration using the volume given in the question. The volume is 2 decimeters cubed. Just use this way equation we've used before. Concentration is number of moles divided by volume. So I'm taking these moles values from this row, dividing them all by 2, and that just goes on into the last column. That's the equilibrium concentration of each one here. Once I get there, I'm pretty much set for the calculation. I've already worked out my Kc value, and I'm just subbing in these values for the concentration. So it comes 0.0003 squared on top, because that's what this Kc expression said. Then the bottom 0.0235 times by 0.00455 cubed. Plug it in and get my answer. Now remember, the units I've had to derive myself, so again, doing the wee working out. So it's moles per decimeter cubed squared over moles per decimeter cubed to the power 4, which is moles per decimeter cubed to the minus 2, which is just moles to the minus 2 decimeters to the 6, which is how I work out my units for the end there. In terms of significant figures, just thinking about the question does give me significant figures, gives me 2 significant figures, so probably maybe left this a bit too detailed. Maybe I should have just given this as 77, so I have to be careful with them as well. But hopefully you follow the maths there. So that's what we probably call a standard example. Again, I'm not saying that's necessarily easy, but there's kind of a nice structure to it. If you follow through the steps, you should get towards the answer, and you'll get a wee bit of practice with the question to see if you understand that. What we're going to go on to on the next page is a couple of very slight variations, which have pretty much the same method, but a couple of things that might catch you out or confuse you. So just going to look at them now. So 2 variations, one where you're not giving a volume to work out concentrations, and one where you're not actually giving any mole values at all for the reaction taking place. So, second example, you're not giving any volumes, because this question looks at first glance to be exactly the same. You've got an equilibrium kind of equation between NO, nitrogen and oxygen. Calculate Kc for the reaction, should say above. At a certain temperature, if 5 moles of nitrogen monoxide gives 1.5 moles of nitrogen equilibrium. So it looks kind of similar. I've got some mole values at the start and the equilibrium. But what you notice is missing here, I've not been given any value. There's no decimeters cubed for this reaction. So from what I said before, that maybe makes it sound like this question is impossible. You can't do it if you can't get equilibrium concentrations. There's one exception to what I just told you. You are allowed to do Kc with mole values as opposed to concentration values if Kc has got no units. So if I just prove that to you, so in this equilibrium reaction, on the top line, so Kc will equal N2 times by O2 over NO squared. Working at the units for that, so that's going to be moles per decimeter cubed squared, because it's times by each other, divided by moles per decimeter cubed squared, because that's squared. So it's going to cancel out. There's no units in this Kc expression. The implication for that, and this is only going to work, there's only a rule if Kc has no units. The one we looked at in the last page did have units, so we couldn't use this rule. You don't actually need to convert into concentrations. You can just use mole values. Now, you can just take that as read and just believe me. A few of you might be scratching your head a wee bit with that, thinking, how could that be possible? The reason is this, if I quickly try and show you. So if I try and convert this Kc, do it up here, into expressing these concentrations as moles over divided by volume. So what I mean by that is, if I was breaking up a wee bit more, the concentration of nitrogen, for example, is the moles of nitrogen divided by the total volume. The concentration of oxygen is going to be the number of moles of oxygen at equilibrium divided by the volume as well. And then for the last bit, the concentration of NO will be the number of moles of NO over the volume squared, because that's what's in the Kc expression. The effect of having no units to your Kc means the volumes actually cancel out, because I could rearrange this into this, so I could just do number of moles of N2 times by number of moles of O2 at equilibrium divided by number of moles of NO all squared, and I could just take the volume values at the other side and be V squared over V squared, which does cancel out. So that's why I'm allowed to, even though it's kind of abusing the Kc expression because they have concentrations, I am allowed to just use moles in this case. So sorry if you got bogged down in that. The take-home message is, when you've got an expression or question where they've not given you a volume, it's probably because the Kc expression has got no units. In this case, you don't actually need to convert the moles into concentration. You can just use the moles value. So as we'll see, so I just do the working out here. The first step in every question is to transfer my values into my table. So I start with 5 moles of nitrogen monoxide. Initial moles is 5.0. I can safely assume that they've not told me about any products at the start, so probably have nothing of them at the start. However, at the end of the reaction, I've got 1.5 moles of nitrogen, so equilibrium moles of nitrogen is 1.5. So that's everything I've got from the questions. I have to use my kind of logical skills here. So let's think about the one I've got 2 values for. I started with no nitrogen. I've now got 1.5 moles of it. Therefore, I've created 1.5 moles of nitrogen. Looking at my equation again, it's a 2 to 1 to 1 ratio in terms of moles. So if I've made 1.5 moles of nitrogen, 1 to 1 ratio, I must also have made 1.5 moles of oxygen. Going the other way, if I've made 1.5 moles of nitrogen, 2 to 1 ratio or 1 to 2 ratio going this way, I must have used up twice the number of moles of NO. So in other words, I've taken away 3.0 moles of it. Again, that can be tricky, so let's looking back the other direction. If I had 3 moles of NO reacting, and I wanted you to work out how much N2 and O2 I make, you would use a 2 to 1 ratio, divided by 2, that would be 1.5, and a 2 to 1 ratio, divided by 2 be 1.5. So it makes sense looking at it as a whole picture there. Again, the tricky step is just trying to work backwards to work out those values. So I've worked out what's taking place within equilibrium. I know what's reacted. I need to work out my equilibrium moles though. So I started with 5 moles of N2, I've used up 3, therefore I must have 2.0 moles remaining. With oxygen, I started with nothing, I made 1.5 moles of it, therefore I've got 1.5 moles of it at equilibrium. Now the key step here, just to re-emphasize again, because I didn't have any units to my Kc expression I worked out at the top, therefore I can just chuck these values into Kc, even though it's strictly speaking not correct because they're not concentration values. So in this case, Kc equals the concentration of N2 times concentration of O2 over NO squared, but I'm just going to ignore concentration, just going to put moles in. So it's going to become 1.5 times 1.5 over 2.0 squared. Type that into my calculator, end up with 0.56. Again, I've got two significant figures here, so leave my answer two significant figures. And it looks like I should put units in, but remember, we emphasized many times, there's no units to this Casey expression, so my answer is just 0.56. That's just the answer. Now that second variation involves a lot of talking. This one's a little bit simpler, the last one, so when you're not giving any mole values at equilibrium. So in this question here, I'm just actually going to sketch out the table because it makes it easier to see what's going on. So we've got a column for HI, so this is how you would do it yourself. It's going to H2 and I2. I need my initial moles. I need my reacting moles. I need my equilibrium moles. Now let's just check, do I need equilibrium concentration? If I do my Casey expression, just quickly to work that out at the top, it's going to be H2 I2 over HI squared. Note this looks like 1, where I've not got any units to Kc because I've got the same kind of concentrations on the top and the bottom. So therefore I don't need equilibrium concentration, I'm safe to use equilibrium moles, and I see that I've not actually been given any volume here, so that backs that up. So let's look at what's a bit sneaky about this question. So the start kind of looks the same. I've got 1 moles of HI to start the equilibrium, so I'm going to put that in 1.0. But they don't give me any equilibrium moles. They just tell me that HI has undergone 22% dissociation. So that's a wee bit tricky to kind of understand that. What that means is 22% of the moles of HI at the start have reacted or dissociated or broken up. So I need to work out how much 20% of 1 is. So it's going to be 0.22 times 1, which is obviously 0.22. So that's the amount which is dissociated. In other words, that's the amount that's reacted. And that would go in this bit here. The reacting moles of HI, I've taken away because I've used it up, is 0.22. That is actually enough to work out the rest of the table. Because using my ratio from the equation, remember it's a 2 to 1 to 1 ratio, if I have used up 0.22 moles of HI, 2 to 1 ratio, I must have made 0.11 moles of H2 and also 0.11 moles of I2 using the ratio. Assuming at the start I had no moles to begin with, because it didn't tell me I had any moles of the products to begin with, I've now got everything I need to get the equilibrium moles. 1, taking away the 0.22 moles that reacted, gives me 0.78 moles. With these two, I start with nothing, so the equilibrium moles is just 0.11 and 0.11. So at this point, again, there's no tricks. I've worked out the trick with the percentage. I'm just going to plug these values into Kc, and just to re-emphasize again, I normally would have to turn that into a concentration because that's what Kc has in it. But because there's no units to Kc, I'm safe to just use the moles there. So Kc, using what I have at the top there, H2 is 0.11 times by I2 is 0.11 divided by 0.78 squared, which gives me 0.020, which is the two significant figures, because at the start I've got two significant figures there. So that's the gist of these Kc calculations. So most of them will look like the ones you found on page 30. So just working through getting equilibrium moles and equilibrium concentration, and then put something into Kc. But we've looked at a couple of variations that can make it a little bit trickier, where you've got no volume given, or you're given like a sneaky little dissociation percentage rather than equilibrium mole values.